in my opinion here, can you move over to the side a little bit, Tim, or sit down? There you go. In my opinion, this is mostly challenging because of the notation, in my opinion. So what are you doing here? You're taking a partial derivative of a function after you have already taken a partial derivative. The hardest thing to do, in my opinion, is keeping track of which one to do first and which one to do second. So what do you think fxx equals? What do you do first? The partial derivative with respect to x, and then you do the partial derivative with respect to x. Hey, so fyy, partial derivative with respect to x, and partial derivative with respect, y, and then partial derivative with respect to y. You're like, wait a minute, that seems counterintuitive. So now you have to figure out, see if you can figure it out. Which one do you do first on fxy, and which one do you do first on fyx? Which one goes first, do you think? And there's a hint right there down below. Which one? Look right here. It says fxy. That means, what do you think you do first? Which one do you think you do first? Which one do you think you do first? Partial z, partial x, it seems like. It seems like that one's first. And then this is what? Second. So let's see if that matches what the work is on. So it looks like what you do first, it matches what you did in Algebra 1. What's the first word of PEMDAS? Parentheses. The challenge is writing the parentheses the right way, right? So the idea here is that's first, and the y is second. Let's see how some of the work is done here. So here's one example problem. So here is a multivariable function, y squared plus 6xy. And this question is asking for computing the compute the 4 second-order partial derivatives. There are 4 of them. There's xx, xy, yx, and yy. So let's look at the ones that are fxx. That one's pretty straightforward, which is you do the partial with respect to x, and then you do the partial with respect to x. So this is the partial with respect to x, and that's what you're doing to it. What's happening here? What is this right here? Y squared 6xy, 6x e to the y. Which one is that? That right there, see this right here? What happens if we do partial z with respect to x of xy squared plus 3x squared plus e to the y? What is that? It is that, right? This is right there. So which one did we do first? We did the with respect to x, and then what? So again, that was first, and this was what? Second. So there are 2 more second-order partial derivatives for this one. What are they? Not the answer, but what are the ones you have to calculate? F, y, y, x, y. That's going to be something. And what's the other one? F, y, x, x, y. Figure out those 2 with your partner right now. Figure out those 2 with your partner right now. Proper notation. If we were going to do this with super proper notation, you're doing fy and then doing the derivative again, like that, with respect to y. Oh, good, I did unfreeze it. Excellent. So if we were going to do perfect notation here, what is fy of the original function? What's fy of the original function? Wait, hold on. So the original function is up here. If you can't remember, it's right up there, everybody. So fy is going to be what? 2xy plus 3x squared e to the, right? So then what are you doing to that? You then need to do the partial with respect to y of 2xy plus 3x squared e to the y. That's what you're doing, I think. So that's going to equal, you're doing the partial with respect to y. What is it? 2x plus e to the? Who agrees with that? Who thinks this is okay? Is that good? We good with that? Nice. So over here, what are you doing first? Fy and then x. So what do we know? Fy? What's fy? 2xy plus 3x squared e to the y. So then we need to do the partial with respect to x of this thing. So write it out. And now when you get this, you do the partial. X is moving. What is it? 2y plus what? 6x e to the y. I think that's right. Is that correct? Who thinks that's right? Who thinks that that's right? Is that cool? Ah, exactly. So you see how I wrote in the specific functions at each point? Please do at least this. It is super easy. It is super easy to miss something and then be really, really unhappy. But at the moment, we're kind of maybe like this. Is that where we're at right now? Or are we like happy like this? Something like that? Okay, nice. Yeah, so what you just noticed on this example, you just noticed that fxy, in this case, equaled f what? Now, we haven't proven that, but is that something you can use? Yes, that is something you can use. It's always true as long as it's continuous there. As long as it's continuous. It should be relatively straightforward to do fx12. What are you keeping steady? What's not changing? What is fixed in this one? What's fixed? What is? Y is fixed, right? So we're going to the point 1, 2. Where's 1, 2? It's this one right here, correct? There's 1, 2. Everybody's with me? So these are y values, right? Those are y values, and these are what? X values. So what are we doing here? You're going forward and backwards. You're keeping y fixed. You're keeping y fixed. So y fixed is the 2 value. That's this one, right? So what do? You're doing 9.6, which is right there. And what are you subtracting? Where's 8.0? Oh, they just went forward one. I see. They went forward one. So there's the 8.0 right there. Nice. And then how far forward did you go? Just 0.1, right? So that's fx. That's 16.0. But then, what's this right here? fx22. What's that? What's that? 88. And there's the 10.65. There's the 12.88. And then there's the 10.65. So what did they end up with? 2 of them. They ended up with 16.0 and? So what does it mean to do fxy? You're doing, which one do you do first? Fx, and then you do what? You do y second. You do y second. So let's take a look at what happened here. So what is that going to be? It's going to be this change right here, and then what are you going to subtract from it? That change right there. And why is it 0.2? It changed by what? 2.2 minus 2? Where's that from? Show me. Go up to the board and point to some numbers for me.